Assalamu alaikum. Today we are going to study the part 2 of atomic structure. So the topic 2.4 is determination of electronic configuration of atoms and ions with proton or electron number and charge. So in order to determine the electronic configuration of atoms and ions, you need to consider the number of protons and electrons in an atom or ion. Note that in neutral atom, proton number or atomic number is equal to the number of electrons. The electronic configuration can be determined by following three steps. First step is the identification of the neutral atom's electronic configuration. Each neutral atom has a specific number of electrons which can be found in the periodic table of elements. For example, a neutral fluorine has 9 electrons. Then you have to determine the charge of the ion. Ions can be positively or negatively charged depending on whether they have gained or lost the electrons. Positive ions have a deficit of electrons while negative ions have an excess of electrons. So positive ions are basically the cations. So these are those that have the positive charge, so they are deficient in the number of electrons, while the negative have excess of electrons. Then write the electronic configuration for the ion. For cations, start with the neutral atom's electronic configuration and remove electrons equal to the magnitude of the positive charge from outermost shell to create the ionic configuration. For anion, start with the neutral atom and then add those electrons. That is given as the negative charge in the outermost shell. For example, the electronic configuration of fluorine is 1s2, 2s2, 2p5. So if we have the F minus 1, so we will write it as 9 electrons plus 1 more electron. So that is 10 electrons. So the electronic configuration will become 1s2, 2s2, 2p6. So if we talk about the cation, that is Na positive. So 1s2, 2s2, 2p6, 3s1 is the normal electronic configuration of the sodium, which has 11 electrons. Now if we use the concept of Na positive ion, so we will remove 1 electron. So 11 minus 1 is 10. So the electronic configuration will become 1s2, 2s2, 2p6, 3s2 and I think it's wrongly written here. The electronic configuration will become 1s2, 2s2 and 2p6. Alright. Then the explanation of electronic configuration in terms of energy of electrons and inter-electron repulsion. The relationship between inter-electron repulsion and electronic configuration is that electrons tend to minimize repulsion by occupying their own separate orbital, rather than sharing an orbital with another electron. So the electrons tend to minimize the repulsions. So therefore, they want to reside in the separate orbital with the same spin, as we studied in the Hund's rule. This is because electrons repel each other due to their identical charges, and this repulsion is minimized when electrons occupy separate orbitals in the same subshell. This repulsion between electrons increases with the increase in the number of electrons in the same orbital, leading to a high energy for larger orbitals. Orbital energy. The energy of an orbital depends on its distance from the nucleus and electron-electron repulsion it experiences. So the energy depends on the distance from the nucleus and number 2 on the electron-electron repulsion. Orbitals with lower energies are filled before those with higher energies. So we studied it in the principle, and that was the Aufbau principle, where we studied that the orbitals with the lower energies will be filled first, then the orbitals with the higher energies. Spin pairing repulsion. Electrons with similar spin repel each other. This is called spin pair repulsion. So the electrons that have the similar spin, they will repel. Electrons therefore occupy separate orbitals in the same degenerate subshell to minimize this repulsion and have their spin same. Hund's rule. Writing the electronic configuration. Electronic configuration of the elements can be done by filling of electron from lower energy level to higher energy level. The table below only represents the electronic configuration in principal quantum number and azimuthal quantum number. Magnetic quantum number and spin quantum numbers are not being shown in the configuration. For example, the configuration 3p6 will mean that it has 3px2, 3py2 and 3pz2. Again, the two electrons should be written as having clockwise and anti-clockwise. So basically we write the principal quantum and the azimuthal quantum number in the electronic configuration. Magnetic and spin, usually we don't show them in the electronic configuration, but we can convert that that in the 3p6, like we have 3 orbitals of p maximum, 3px, 3py and 3pz, and each orbital has the 2 electrons maximum. They will have the opposite spin, like in the clockwise and the anti-clockwise. So that's we infer from the from that electronic configuration. If an element is having atomic number 25, its electronic configuration will be written as follows. So 25 is electronic configuration showing all the quantum numbers: 1s2, 2s2, 2px2, 2py2, 2pz2, 3s2, so up to so on to 3dz. Okay, then we have these electronic configurations in this table. So they have written it according to the atomic number. Now the topic that is very important in this chapter is shapes of orbital. So orbital is basically the region in the space where the probability of finding electron is maximum. Different orbitals have different shapes in 3-dimensional space. P orbital has 2 lobes and D orbital has 4, except dc square, and S orbital is spherically symmetrical. So the shapes of these orbitals are shown. S is spherical, P is dumbbell shaped, and D is cloverleaf, and F has complicated shapes. So these are the shapes. Like in the first picture we have spherical shape, then the next 3 pictures are for the p orbitals, and in the last line we have 5 pictures that are showing the orbitals of D. Then we have the free radicals. Free radical in an atom or molecule with an unpaired electron in its outer shell. Free radical is that atom which do not usually take part in the reaction. This makes it highly reactive and capable of immediate reactions. They are activated atoms or molecules, so they're very reactive, highly reactive, and they perform immediate reactions. The electronic configuration of free radicals is the same as those of atoms. Chlorine, CH3 and Br, but we have to show a dot on them to show that it's a free radical. And we have the concept of ionization energy. The minimum energy needed to remove the outermost electron, that is the most loosely bound electron, from the gaseous isolated atom. Na gives us Na positive plus 1 electron, and the ionization energy will be 496 kJ per mole. Magnesium gives us Mg plus 1 electron. So in the next one, when it loses 1 more electron, then it will convert into Mg2 plus. So the ionization energy, first ionization energy of magnesium is 738 kJ per mole. Basically, is the minimum amount of energy that is required to remove the outermost electron from the gaseous isolated atom. Atom is needed to be in the gaseous state to avoid the influence of other factors like heat of fusion, bond dissociation energy, heat of vaporization. So the gaseous state is the state in which there are less influence of the other factors like the heat of fusion and bond dissociation and the heat of vaporization. That's why we are using the atom in the gaseous state, and should be isolated so that it may not interact with other atoms, and if it's isolated, then it will be easy to remove the electron from the outermost shell. Then we have periodic trends of ionization energy. Ionization energy generally increases from left to right in a periodic table with slight anomalies. This is due to increased number of protons in each step, which strengthen the attraction of nucleus in one electron. Electronic configuration also affects the ionization energy. In group number 3a, less ionization energy observed as there is only one electron in p orbital, which is unstable configuration. Instead, in group 5a, greater ionization energy values are observed. This is due to half-filled p orbitals. So half-filled p orbitals are stable as compared to 3a, that is unstable. From left to right in the main group element, shielding effects remains constant, so there is no effect on the ionization energy values in this respect. Atomic radius decreases from left to right, which brings the electrons near to the nucleus. Thus, attraction is increased, so does the ionization energy. In a group from top to bottom, ionization energy decreases. So basically, from left to right, ionization energy increases in a period, and from top to bottom in a group, the ionization energy decreases. As the size of an atom gets bigger, the valence electrons goes away from the nucleus, and the shielding effects keeps on increasing, and it will be easier to remove the electron from the outermost shell. Then we have the factors that are influencing the ionization energy. First one is the nuclear charge, second one is the atomic radii, third is shielding effect, and fourth is spin pair repulsion. So what is nuclear charge? As the nuclear charge increases moving from left to right in the periodic table, the attraction on the outermost electron also increases, which in turn will increase the ionization energy. So this is just according to the Coulomb's law. Atomic radii moving from left to right in the periodic table decreases the radii, which strengthens the attraction of nucleus, so the ionization energy increases. From top to bottom, size increases, ionization energy decreases. Then we have the effect of shielding. The shielding effect plays a significant role in the influencing ionization energy. As you move down a group, the number of electron shells increases. The inner electron shell acts as a shield, reducing the effective nuclear charge felt by the outer electrons. The shielding effect makes it easier to remove outer electrons, leading to a decrease in ionization energy down a group. From left to right, shielding effect remains constant and poses no effect on ionization energy. So basically, in the group, the shielding effect comes, and it will definitely influence the ionization energy. So there is a large shielding effect, so the ionization energy keeps dropping in a group. Spin pair repulsion. When electrons are paired in half-filled p orbital, there is electron pair repulsion, which causes the energy of the electron to increase. Increased energy makes the electrons easier to remove, and therefore the ionization energy decreases. For example, there is slight decrease in the ionization energy going from nitrogen to oxygen in the second period. So when electrons are paired up in the half-filled p orbitals, so their energy is very high. So it's very easy to remove that electron. So ionization energy decreases. So when we, in a period when we move from nitrogen to oxygen, so this is basically the reason the electrons are paired up and there is a slight decrease in the ionization energy. As we move across a period, the effective nuclear charge increases, drawing electrons closer to the nucleus, but spin pair repulsion counteracts the increased nuclear attraction, making it slightly easier to remove the electron. So these are the factors that contribute towards the ionization energy. Next topic is the reduction of position of an element in the periodic table by using ionization energy data. To deduce the position of an element in the periodic table using successive ionization energy data, we can analyze the trends in the ionization energies and compare them with the known periodic table. Ionization energy is the amount of energy required to remove an electron from a neutral atom, resulting in a positively charged ion. So trends, again we have the trends that ionization energy generally decreases top to bottom and increases from left to right, with few exceptions, like the first ionization energy decreases from beryllium to boron and magnesium to aluminium. This is due to the 3A exceptions. Then periodic table organization, that the periodic table is organized in a way that elements with similar ionization energies are grouped together in the same column. This organization is based on the electronic arrangement of the elements, which determine their chemical properties. Then we have the comparing ionization energy. To determine the position of an element in the periodic table, we can compare its ionization energies with the periodic table. If the element's ionization energy match the expected values for its position in the periodic table, we can confirm its position. So it's very easy to determine the position of the element in the periodic table with the help of ionization energy. For example, let's consider the element with the symbol X. This element will be located between its higher value and its lower value, keeping the lower value element on the left and the higher on the right. For example, if the ionization energy of an element is 1251, it will be placed between sulfur and argon, which have ionization energy values of 1000 and 1520. Similarly, from top to bottom, if element has the ionization energy of 738, so it will be placed between the calcium and beryllium. So it's easier to locate the position of an atom by placing it between those elements that have the similar values of ionization energies. This method is not always accurate, but there is some fluctuations in the ionization energy, but yet it's a very important method to locate the position. Now we have the next topic, that is electronic configuration and position in the periodic table by using successive ionization energy data. Okay, moreover, the successive ionization energy values in index of the valence of an atom. Big gaps show that next electron is being removed from the lower shell. For example, in the case of sodium, there is a big gap of first and second. First ionization energy is 495 and second is the 4560 kilojoule. So this indicates that there is only one electron and this element must be a part of group number 1. Because there is such a huge difference between the ionization energy between the first ionization and second ionization. So this is the possibility that there is only one electron in an atom that would be removed. Similarly, in case of magnesium, we have the first ionization energy 735, then second is 1445, and then there is a huge gap between the second and third, that is 7730. So it means that in the magnesium only 2 electrons will be removed. So the ionization energy values also give us the information about the number of electrons that will be removed and about their positions as well. This indicates the third electrons being removed from the inner shell. It indicates that there are only 2 electrons of valence shell which are removed easily. So this element should be a part of group number 2. So that's how we can also calculate, we can also know about the position of the atom in the periodic table with the help of ionization energy. Then we have the very important topic of this chapter, that is mass spectrometry. Mass spectrometry is a powerful analytical technique used to determine the molecular composition and structure of a sample by measuring the mass to charge ratio. It is widely used in the various scientific fields such as chemistry, biology, and physics. Principle of mass spectrometry. So mass spectrometry involves 3 fundamental steps. Basically, it's an analytical technique and it is used to determine the molecular compositions and structure of sample. And we measure basically the mass to charge ratio, and it has 3 fundamental steps. First is ionization, second is mass analysis, and detection. So the sample is first ionized, converting its molecules into ions. These ions are then separated based on mass to charge ratio and detected. So then the mass spectrum will be made and the observer can observe it through the computer screen, which provides information about the composition and abundance of the sample, molecule or isotopic composition. So how it works? So basically, first step is the ionization. We have the ionization chamber in which the sample is introduced, and how ionization will occur. So we will bombard the high energy electrons introducing to a high voltage fields, and we can also use laser to vaporize its matrix assisted laser desorption ionization, and it's commonly known as MALDI. Then we have the ion separation. In the ion separation, the resulting ions are accelerated and directed into the mass analyzer. The mass analyzer separates ions based on the mass to size ratio, allowing ions of the different masses to be focused and detected at different times. Then we have the detector. So as the ions exit the mass analyzer, they hit the detector. Detector records the time it takes to ion to reach it, and this data is used to calculate the mass to size ratio of each ion. Then we have the data analysis. The information collected from the detector is used to construct a mass spectrum. The X-ray of the spectrum represents the x-axis of the spectrum represents the mass to size ratio, while the y-axis represents the abundance of ions. So at the x-axis we have the mass to size ratios, and on the y-axis we have the abundance of ions. Peaks in the spectrum correspond to different ions present in the sample with their position revealing their masses. So it's a basis of the mass spectrometer that we have that ionization chamber, and then we have the mass analyzers, and we have the detectors at the end. So how it works? We have the applications of mass spectrometry. Mass spectrometry has a wide range of applications, including relative abundance of isotopes of an element, identifying unknown compounds, quantifying the amounts of specific substances, elucidating molecular structures, and studying biomolecules like proteins and nucleic acids. The average atomic mass of an element can be calculated by using the following formula, taking into account the relative abundance: mass number into relative abundance plus mass number into relative abundance divided by 100. So it's a formula for calculation of the average atomic mass. So we basically calculate the relative abundance and identify the unknown compound, or basically we can calculate the molecular structures, we can elucidate them, and we can also study the proteins and nucleic acids. Non-integer relative atomic mass. Usually the atomic masses written in the periodic table are not in integral number. These non-integral atomic masses are the result of inclusion of relative abundance of different isotopes. Relative abundance is usually taken in percentage units. They are multiplied by the mass number. Its summation is divided by 100. So the chlorine has two isotopes. For example, we have the chlorine 35, chlorine 37, and their abundances are 75.76 and 24.24. So what we will do, that we will multiply the 35 with the 75.76 plus 37 into 24.24 divided by 100. So it will equal to 35.48 AMU. We will basically multiply the atomic masses with the percentage of each, and we will add them together, and then we will divide it with 100. Then we have the electronic configuration of modern electronic materials. Semiconductors are basically the modern electronic materials, and these are the materials that possesses electric conductivity between that of conductor and insulator. The electronic configuration plays a crucial role in determining their behavior. Let's consider silicon as an example. Silicon has an atomic number of 14, meaning it has 14 protons and 14 electrons. The electronic configuration of an element describes how these elements are distributed. So silicon is basically used in the semiconductors and it has atomic number of 14. So we will write the first energy level will hold 2 electrons, 1s2. Second will hold 8 electrons, 2s2, 2p6, and the third one has 4 electrons, 3s2 and 3p2. So role of electronic configuration in determination of type of semiconductor. In silicon, the outermost energy level is the third energy level. The 3s and 3p sublevels together can hold a maximum of 8 electrons. However, in its ground state, silicon has 4 valence electrons, which are the electrons outermost shell. This configuration gives silicon unique properties that make it suitable material for semiconductor. So basically, it's all about the electronic configuration of the silicon that helps to make it a good semiconductor. So how that we are going to see it further. The arrangement of silicon electrons creates a band structure. In the valence band, electrons are tightly bound to atoms and cannot move freely. In the conduction band, there are no electrons in the ground state. However, due to relatively small energy gap between the valence and conduction band, that is referred to as band gap, electrons can be promoted from the valence band to conduction band, creating electron hole pairs. This process is called excitation. So basically we have the two bands, the valence band and conduction band. So in the valence band, the atoms are tightly bound and they cannot move freely, and in the conduction band there is no electron. But due to the small energy gap, and when we provide a small amount of heat, the one electron from the ground state will move to the from the valence band to the conduction band, and this process is known as excitation. Semiconductors can be extrinsic and intrinsic. Intrinsic semiconductors are pure materials like silicon or germanium, while extrinsic semiconductors have controlled impurities intentionally added. So intrinsic are the pure and the extrinsic are impure ones. The impurities are called dopants and can either introduce extra electrons, n-type, or create holes that behave like positive charge carriers like p-type. So in the n-type we have extra electrons, in the p-type we have the holes or the protons as a charge carriers. This process is known as doping and is achieved by substituting some silicon atoms with other elements like phosphorus in case of n-type and boron in case of p-type. The special electronic configuration of silicon makes it able to either accept or lose the electron. So silicon can work as n-type or p-type semiconductor. Means it can also gain 4 electrons or it can also lose its electrons. For example, if silicon is doped with phosphorus, silicon will be n-type, electron acceptor. And while doping with elements like boron makes silicon p-type, electron donor. In n-type semiconductors, dopants introduce excess electrons that can move freely in the conduction band, improving electrical conductivity. In p-type semiconductors, dopants create holes in the valence band that can move, effectively behaving as positive charge carriers. By strategically combining n-type and p-type materials, engineers can create diodes, transistors, and other electronic components that exploit the unique properties of semiconductors to control the flow of electric current. So this forms the basis of modern electronics and technology. Thank you so much.